Something impossible unfolded on the far side of the Sun. At 7:47 a.m., Eastern, October 29, 2025, the interstellar comet 3IATLAS brushed past perihelion, its nearest point to our star, just 203 million kilometers from the solar surface. For the first time in 10 billion years, a fragment from another age tasted sunlight again. Then, for 8 long days, it vanished. The sun swallowed it in glare. Every telescope on Earth went blind. When it disappeared, the silence that followed was not ordinary cosmic silence. It was heavy, expectant, like the pause before an answer that never comes. In those final hours before vanishing behind the solar disk, something inside the comet changed. Its brightness began to spike, first steadily, then exponentially. Within hours, it blazed brighter than physics should allow, glowing a blue-white hue hotter than the sun itself. Astronomers stared at the spectral readings in disbelief. A comet should be freezing, hundreds of degrees colder than the photosphere, yet this thing emitted light, as if burning hotter than the solar surface. 8 days later, NASA's Punch satellites caught the first frames of 3IATLAS emerging from the solar glare. The orbit matched the predictions perfectly. No deviation, no course correction, no gravitational slingshot aimed toward Earth. At least that's what the public data said. But within the blacked-out intervals of those observations lay missing chapters. China's Purple Mountain Observatory, which had tracked the object daily through August and September, abruptly halted updates right after its close pass by Mars. NASA holds unreleased high-resolution photos from the Mars Reconnaissance Orbiter taken when the comet swept within 30 million kilometers of the red planet. Scientists requested them, Harvard's Avi Loeb among them, but the response has been silence. It's a pattern that repeats whenever reality stops fitting its box. The fragments of data we do have already break every comfortable rule. Even stripped of speculation, the numbers are wrong in ways that make mathematicians uneasy. First, its path. 3IATLAS isn't tumbling randomly through space like most interstellar drifters. Its orbit hugs the ecliptic plane, the thin cosmic sheet where all major planets circle the sun, within 5 degrees of alignment. The chance of this being pure coincidence? About 1 in 500. It also passed close to Mars, Venus, and Jupiter in precise sequence before looping directly behind the sun, perfectly timed to stay hidden from Earth. Stack those probabilities, and the odds plunge below 1 in 100,000. Then there was the sunward jet. Comets release material away from sunlight. Solar radiation pushes dust outward. But for nearly 6 weeks, 3IATLAS vented gas straight toward the sun. Hubble confirmed it. Ground-based scopes confirmed it. The tail defied the laws of radiation pressure until early October, when the jet reversed and began behaving normally. What could possibly make a comet reverse its outflow direction? The textbooks have no answer. Spectroscopy added more confusion. Instruments detected a strong signature of nickel, about 4 grams per second, vented into space, but almost no iron. In nature, iron always dominates over nickel by an order of magnitude. The ratio here matches industrial alloys, not stellar chemistry. The probability of such a ratio occurring naturally? Less than 1%. The water fraction was equally wrong, only 4% by mass, where most comets are 70% ice. Even the way light scattered from its coma produced extreme negative polarization, another statistical impossibility. Each anomaly might be dismissed alone, but together they paint a picture that refuses to behave like anything born of chance. And then there's the eerie connection to the 1977 WOW signal. The narrowband radio pulse that once flared across the Big Ear telescope came from nearly the same patch of sky, within 9 degrees of 3IATLAS's inbound trajectory. Coincidence? Perhaps. But combine all those odds: trajectory, timing, jet direction, metallic ratios, miss in iron, water deficit, polarization, and spatial correlation, and you reach a cumulative probability near 1 in 10 quadrillion. You'd have a better chance of winning the Powerball lottery 30 million times in a row. Still, scientists preach restraint. Extraordinary claims demand extraordinary evidence, and the rational stance remains that 3I-ATLAS is a natural wanderer, a survivor of a bygone stellar system now drifting through ours by sheer happenstance. Yet even the skeptics admit its behavior strains the models of comet physics to the breaking point. As the comet neared the sun, its luminosity skyrocketed, but not in the way expected from gradual heating. Normally, a comet brightens in a predictable curve as volatile ices vaporize. Here, the brightness increased according to an inverse distance law raised to the power 7.5. That's not linear. That's exponential insanity. For a body with only 4% water, frozen for billions of years, it shouldn't have had the energy to glow like that. Observatories from Stereo A to Soho saw the same thing: a halo extending 300,000 kilometers, nearly the Earth-Moon distance, surrounding the nucleus. Then came the strangest observation of all: color. Data from Soho's LASCO coronagraph and the GOES 19 CCR1 instrument revealed the light from the comet was bluer than sunlight itself. In thermal physics, blue means hotter. For the emission to shift that far, the source temperature would have to exceed 5,800 Kelvin, the sun's surface temperature. No natural comet surface reaches anything close to that. Scientists scrambled for explanations, maybe fluorescence from excited cyanide molecules. But fluorescence can't dominate brightness on that scale. Perhaps highly reflective ice? Impossible. The comet's ancient surface should be darkened by radiation, not mirror bright. The conclusion no one wanted to say aloud began creeping into conference halls. Either our understanding of cometary physics is incomplete, or something inside the comet was generating energy, an internal heat source, an engine. No one's claiming 3I-ATLAS is a machine, but the pattern of its behavior, thermal emission beyond natural bounds, compositional irregularities, structural endurance, resembles not randomness, but design. If you were to send a probe across interstellar space meant to endure 10 billion years, you'd make it dense, resilient, and capable of harvesting energy from stars it passes. A close solar flyby would be a perfect refueling maneuver: absorb radiation, convert it into power, perhaps correct trajectory using gravitational assists. That's exactly the path 3I-ATLAS followed. Yet, according to every trajectory model, it made no active course change, no thrust, no deviation, just an elegant, gravity-perfect arc. So maybe it isn't here for us. Maybe it's following a script written eons ago, looping through systems, observing silently, then fading back into the dark. Or maybe it's just an impossibly strange, natural relic from the universe's youth. But that blue light, hotter than the sun, from a body colder than ice, still hangs in the data like a whisper that something's off. The old sunward jet had vanished by the time it reappeared from behind the sun, the plume now pointed properly away, as if the comet, or whatever it is, had been corrected during those hidden days. We don't know how, or by what. The Mars orbiter images remain locked away. China's data gap grows harder to explain. All we have is a before and after, with the middle missing, the very moment when the rules broke most spectacularly. That's where the story begins to feel less like astronomy and more like archaeology. We're digging at the edges of something ancient, intelligent, perhaps self-sustaining. Scientists like Loeb push for transparency, for every byte of data to be released. Radio observatories are listening for emissions, nothing yet but cosmic background noise. Still, the silence is instructive. True probes might be quiet ones. For now, 3IATLAS continues outward, unchanged in course but changed in mystery. What happened behind the sun remains unsolved. What we know defies what we thought we knew, and somewhere, across that gulf of 8 days, lost to solar glare, perhaps the laws of comet physics bent, not broken by chaos, but by intent. To understand why 3IATLAS feels like a trick question written by the universe, you have to start with its age, 10 billion years. Our sun is less than half that. Earth wasn't even dust when this object formed. Whatever sculpted it did so in a galaxy still noisy with the echoes of the first starbursts, heavy elements newly minted, shock fronts colliding, infant stellar nurseries being torn and remade. Natural comets are the fragile children of quiet times, loose aggregates of ice and dust, stitched together by van der Waals forces, prone to shedding, cracking, and disintegrating after too many warm-ups. The survival odds of a dirty snowball across 10 giga-years aren't low. They're essentially zero. So either 3IATLAS isn't fragile, or it hasn't been through the ringer we imagine. Perhaps both. There's a line of thinking that tries to rescue the natural hypothesis without hand-waving. Repeated cycles of microheating and cooling over eons could sinter grains together, welding pores shut and densifying the body into something monolithic. Cosmic rays can both darken and harden surfaces, turning frost into tougher crust. Interstellar erosion might sand away weak layers, leaving a core that's stronger than the original rubble was. In other words, time might not only destroy, under some conditions it refines. But that still leaves the alignment problem. Why is this interstellar visitor's approach so neatly aligned with the ecliptic? One way to demystify coincidence is to look for bias. Our surveys are better at finding things that move where we're already looking, near the planetary plane, in cadence with existing search patterns, during seasons when the inner solar system is well placed. If the detection pipeline is tilted toward ecliptic crossers, then the improbable becomes merely unlikely. Yet even after you account for bias, the Mars-Venus-Jupiter timing and the sun behind invisibility window feel composed. Like a note that resolves just where your ear expects it to, and you can't decide whether the composer is nature or intention. Then there's the sunward jet, the anti-tail, that refused to obey radiation pressure. In standard comet physics, gas accelerates away from the heat source, dragging dust with it. Sunlight acts like a constant, gentle shove. Reversing that requires either geometry, a trick of perspective, or a force that overpowers radiation pressure. Multiple vantage points kill the geometry excuse. So what's left? Some astronomers have pointed to charged dust grains interacting with heliospheric magnetic fields. If enough particles become electrically charged, they can migrate along field lines in unintuitive directions. The problem is scale. An elegant idea at micron levels needs to move kilometer-scale structures in the coma to match what we saw, and the field strengths aren't obviously sufficient. Another notion, collimated vents, geysers from subsurface reservoirs, can act like nozzles. If the nucleus is rotating, a jet could periodically aim sunward, but that doesn't explain why the behavior persisted for weeks, and then, conveniently, ceased around October. We get pulled again and again back to composition. 4 grams per second of nickel is not a gentle whisper. Across months, that's tens of tons. Metals don't sublimate like water or CO2 at the temperatures we're dealing with. To free nickel into the gas phase, you either need extreme localized heating, micro arcs, shocks, exothermic chemistry in confined pores, or non-thermal processes, sputtering from energetic particles, field-enhanced desorption. The nearly absent iron is the deepest cut. In most stellar forges, Fe and Ni travel together. Seeing nickel alone feels like finding a key with no lock. Something selective happened. If this is a natural planetesimal fragment, maybe differentiation exposed a layer rich in nickel compounds but depleted in iron, a sliver from the boundary of a long-dead core. It's a stretch, but not impossible. The blue emission refuses to be domesticated. Fluorescence can make coma glow, yes. CN bands and other radicals can shift perceived color. But to exceed the sun's apparent color temperature across a broad halo? That suggests either a forest of emission lines stacked where our instruments integrate, or a non-thermal population radiating with astonishing efficiency. A few researchers floated the idea of triboluminescence, light from mechanical stress if crustal plates within the nucleus crack and slip as it heats. Another group speculated about transient plasma, dust grains becoming tiny antennas under intense UV, emitting at shorter wavelengths via collective effects. These are clever, testable ideas. They also underscore how far outside the playbook 3IATLAS has pushed us. At this point, probability math starts dressing up intuition. Stack odd against odd, multiply small chances by smaller ones, and you arrive at a number so tiny it feels like an argument, 1 in 10 quadrillion, but statistics can't adjudicate a sample size of 1. A single Baroque natural outlier does not demand artifice. It does, however, demand new physics within old bounds, mechanisms we haven't modeled, parameter spaces we haven't explored, combinations we've never seen coinciding in one stubborn object. And yet the engine picture lingers because it's narratively coherent. Imagine a probe that budgets energy not for centuries, but for aeons. Chemical stores won't do. Radioisotopes decay. Batteries die. But stars are inexhaustible lighthouses. Swing past one, drink deeply, keep going. In that design brief, you don't build a delicate lattice. You build a bullet, dense, cohesive, tolerant of impacts, radiation, and thermal shock. You include a way to shed heat fast, a bright structured halo, a way to process or vent byproducts, nickel-rich outflow, and a control system disciplined enough to execute gravity-only transfers across the disk of a planetary system without wasting propellant. A machine like that wouldn't chatter on the radio. It would minimize signatures, avoid maneuvers, and let the star do the work. But if we're honest, there's an equally compelling natural counter-narrative. Think planetary shrapnel. Tidal disruption can crack worlds that graze too close to their suns. Fragments from differentiated interiors would carry exotic ratios, nickel pockets, iron-poor seams, volatile depleted matrices hardened by pressure. A shard like that could travel for billions of years, its surface cooked into a tough, low-albedo skin, its vents opening along remnant fractures. The sunward jet becomes a combination of rotation and topography. The blue emission becomes a thicket of lines from unusual metal-bearing molecules or plasma near the vents. The structural integrity becomes inevitable, rock and alloy, not fluff and frost. This story leans on rare events, but the universe is a rare event factory, which leaves the part that feels most like sleight of hand, the missing time. In the blackout behind the sun, the anti-tail died. The plume normalized. The brightness spike crested and fell. We resurfaced on the other side with a comet that looked more ordinary, yet carried the memory of disobedience in its data. Maybe the transition is exactly what you'd expect when a heat wave passes and fracture-driven gazers seal. Maybe it's what you'd expect when a system finishes doing whatever it came to perihelion to do. There are practical tests ahead, and they don't require faith in either storyline. Polarimetry at multiple phase angles can constrain grain sizes in the coma. If the particles are unusually uniform or metallic, polarization curves will show it. High-resolution spectroscopy across visible and near UV can map emission lines to specific carriers. If nickel is present as a particular complex, or if iron truly is absent, the line forest will tattle. Thermal IR mapping can track hotspots and cooling rates. A surface heated by sunlight cools predictably as the comet recedes, while any persistent anomalous glow would stand out like an ember in snow. Precision astrometry can bound non-gravitational accelerations. If outgassing forces are unbalanced, or if anything like thrust is present, the track will betray it. None of this requires conspiracies or leaks, just time and clear skies. Even the probability puzzle can be brought down to earth by better denominators. We've observed only 3 confirmed interstellar interlopers up close. Oumuamua, weird, Borisov, comfortingly comet-like, and 3IATLAS, weird again. 2 strange cases out of 3 doesn't mean 2/3 of all interstellar objects are bizarre. It means our net has only started trawling. Survey bias, cadence, and sheer luck play oversized roles at small n. Within a decade, as newer sky surveys run deeper and faster, we'll have dozens, maybe hundreds, of examples. The distribution of normal versus anomalous will firm up, and probability will stop pretending to be destiny. Still, there's an emotional charge to this one that's hard to dismiss. We are not just measuring a rock, we are eavesdropping on prehistory. When 3IATLAS formed, the periodic table was young in the cosmos, and the Milky Way's arms were busy cannibalizing smaller galaxies. Whatever path brought this relic to our neighborhood passed through regions and epochs no human instrument has ever sampled. Even if it's natural, it's a time capsule from an environment our textbooks cover with 1 paragraph and a shrug. Let's not forget the straightforward, almost mundane victories buried under the mystery. The object survived perihelion without cracking, data point, strong internal cohesion. Its non-gravitational acceleration remains consistent with venting balanced over rotation, data point, no obvious thrust. Its current outbound arc matches predictions, data point, gravity still rules. Those aren't headlines, but they are anchors, the kind you tie to while you test wilder ideas. And if, in the end, the wild ideas lose, if spectroscopy pins the blue sheen on an exotic but natural cocktail of lines, if the nickel story resolves into a geologic quirk of an ancient core fragment, If the sunward jet turns out to be a magnetic party trick that we'll start recognizing in other comets now that we know to look, then 3IATLAS will have done something arguably more valuable than confirming our cosmic fantasies. It will have forced cometary physics to grow up. Paradigms don't need alien engines to change. They need stubborn data. For now, the most honest sentence we can write is also the most unsatisfying. We don't know. Not yet. The object of interest is pulling away from the sun, cooling, dimming, but entering a phase of observation where Earth-based instruments can finally work without the sun's glare bullying them. Every night it offers a little more angle, a little more time on target, a little more signal to noise. The mystery doesn't love us back, it just keeps moving. Our job is to keep up. By mid-November 2025, 3IATLAS had emerged from the sun's glare, and for the first time since its approach, the world could look at it again. The object appeared steady, brighter than a typical comet, but less violent now. The halo it once wore like an electric crown had faded to a manageable aura, roughly spherical, its blue hue diminishing toward a soft, steel gray. To the naked eye through a telescope, it was beautiful. But to the scientists who'd been waiting through those 8 days of blindness, the calm was almost maddening. They wanted turbulence, data, drama, something that might explain the impossible week they'd missed. NASA's Jet Propulsion Laboratory held a closed review on November 10th. Attendees included representatives from ESA, JAXA, and several civilian observatories. According to leaked notes later corroborated by participants, the atmosphere oscillated between excitement and disbelief. The SOHO and stereo datasets were cross-calibrated, and the consensus was clear. The blue emission spike was not an instrumentation error. Neither was the brightness surge. Multiple sensors, multiple platforms, same curve. Something had genuinely happened behind the sun, something that injected a burst of energy equivalent to millions of tons of TNT into the comet's surroundings. But from what? A few proposed the mundane, a major structural collapse, a fragment slamming off and releasing volatile gases. Yet the photometric record showed no debris plume, no splintering nucleus, no trajectory change. The brightness rose and fell smoothly, like a controlled ignition rather than an explosion. Others theorized electrical discharge, cometary plasma interacting with the solar wind in a transient current loop. Still, that couldn't explain the spectral blueness, nor why the effect ceased precisely as the comet reached its closest solar distance. Across the Pacific, China's Purple Mountain Observatory remained silent. For 2 months their channels had gone dark. The explanation, operational reassignment toward lunar priorities, rang hollow. Amateur astronomers who had corresponded with the observatory during the summer reported that updates and collaboration requests suddenly ended after the Mars flyby, as if an embargo had been imposed. Conspiracy theories blossomed overnight. Was there something in those missing images? Had 3IATLAS interacted with Mars somehow, perhaps shedding particles that entered its atmosphere or even scanning it? The speculation felt reckless, yet it was fueled by a vacuum of transparency. Meanwhile, Avi Loeb doubled down. He called publicly for all unreleased datasets to be published, arguing that withholding information about a confirmed interstellar visitor violated the principle of open science. In an editorial for Scientific American, he wrote, "If this object teaches us something new about nature, hiding that knowledge delays discovery. If it teaches us something new about ourselves, hiding that is cowardice. His tone was both academic and accusatory. NASA issued no official response. In the absence of fresh revelations, astronomers pivoted from speculation to methodology. The upcoming JUICE spacecraft encounter offered a lifeline. Though the probe was half an astronomical unit away, about 75 million kilometers, it could still sample the comet's light through its ultraviolet and infrared spectrometers. The plan was to take readings on November 2nd and again on November 25th, covering the period when 3IATLAS's activity was expected to stabilize. Data transmission would take months, arriving only by February 2026, but even delayed answers were better than silence. During this waiting period, the global astronomical community faced a dilemma: how to talk about anomalies without inviting hysteria. The alien probe hypothesis had escaped into public media, spun by podcasts, YouTube documentaries, and speculative journalists. They loved the symmetry, 10 billion years old, surviving impossible odds, aligned perfectly with the ecliptic, glowing hotter than the sun. To a public hungry for wonder, it sounded like revelation. Scientists, however, were cautious. Many remembered the Oumuamua frenzy of 2017, a strange acceleration, an odd shape, a media storm, and then years of sober recalibration. They didn't want to repeat. But silence breeds imagination, and imagination, once unleashed, doesn't obey press releases. Privately, even among professionals, the data gnawed. Why would a comet vent nickel? Why so little water? Why that eerie polarization? When light scatters off dust grains, its polarization pattern tells you about the particle's size and structure. 3IATLAS returned a polarization angle far more negative than any known comet, almost like light bouncing off smooth metal surfaces instead of rough ice or dust. Some researchers wondered whether the grains were unusually uniform, perhaps spherical, like manufactured microbeads. The thought was quietly absurd, yet the math said what it said. Observational data rarely cares about human comfort. At the European Southern Observatory, a working group began modeling nickel silicate composites under interstellar exposure, imagining a scenario where natural sintering could produce shiny, heat-resistant surfaces. They proposed that as a comet ages, repeated microheating could drive metals toward the surface, creating a reflective crust that behaves more like alloy than dust. It was an elegant natural hypothesis, and for a few weeks it looked like consensus might return. Then another anomaly landed on their desks. The SOHO coronagraph team discovered faint radial striations in the halo, visible only in polarized light, concentric shells of varying brightness, almost like interference rings. They weren't artifacts. The patterns rotated with the comet itself, repeating every 6 hours. Structured emission, not chaos. That detail reignited the fire. If 3IATLAS were just rock and ice, what could organize gas and dust into rotating shells 300,000 kilometers wide? Pressure waves? Magnetic oscillations? Something rhythmic was happening deep within the object. The machine whispers started again. Outside the labs, the comet was becoming a cultural event. In online forums, amateur observers tracked its movement before dawn, comparing notes and sharing processed images. It wasn't bright enough to see unaided, but through a mid-sized telescope, it appeared as a faint blue smudge near Venus, a ghostly relic from another star. For a species that had dreamed for millennia about visitors from the beyond, 3IATLAS was as close as fiction had ever come to reality. Poets wrote about it. Musicians named tracks after it. The mystery became myth in real time. Still, professionals tried to anchor the discourse in measurable facts. Every major observatory prepared for the December 19th window when the comet would reach its closest approach to Earth, 269 million kilometers. Hubble, Webb, and the Very Large Telescope were booked for synchronized observation campaigns. The plan: gather every photon, every wavelength, every nuance of data possible. The James Webb Space Telescope would hunt for infrared heat signatures that couldn't be explained by solar warming alone. Hubble would look for surface irregularities. Ground observatories would analyze rotation and outgassing cycles. And radio arrays would listen, not because anyone truly expected a message, but because, as Loeb said, if you never listen, you'll never know what silence really means. Between November 10th and the end of the month, 3IATLAS remained photometrically stable. No more blue flashes, no trajectory deviations, no signs of fragmentation, just a steady decline in brightness as it moved away from the sun. It looked for all the world like a normal comet finally settling down after a bout of cosmic madness. But that stability raised more questions than it answered. Why the sudden calm? Why the perfect behavior now, after defying physics only weeks earlier? Some speculated that perihelion had triggered a phase transition, a chemical threshold that once crossed, locked the comet into dormancy. Others floated darker ideas. What if the event we witnessed was deliberate, a controlled reconfiguration during those hidden 8 days behind the sun? A recharge cycle, a maintenance maneuver, a hibernation switch? The rational mind resists such thoughts. Yet in the face of so many improbabilities, even rational minds begin to waver. By Thanksgiving week, when 3IATLAS was roughly halfway between the orbits of Earth and Mars, ground-based imagery showed the halo contracting. The tail was faint but clean, pointing away from the sun like textbook comet behavior. Nothing unusual remained except, of course, everything. Every number, every ratio, every spectral line. The laws of physics hadn't broken. They had simply been stretched until they screamed. One senior astronomer summarized it perfectly during a symposium in Prague. If 3IATLAS is natural, then nature is a better engineer than we are. The statement wasn't poetic. It was resignation disguised as awe. We might yet find that the object is simply old, dense, and peculiar. But if that's true, then peculiar needs a new definition. By December, the story would pivot again. The comet would reach its closest approach, and humanity would have its clearest look yet. The months of speculation would either unravel or ignite anew, and somewhere within that haze of data, we might finally learn whether 3IATLAS was a cosmic accident, or the echo of intelligence that predates our sun. For now it drifted onward, serene, indifferent, and impossibly ancient, its secrets sealed beneath a shell of nickel frost and time itself. December arrived with a kind of electric stillness. For months every instrument capable of watching the skies had been waiting for this, the moment when 3IATLAS would be closest to Earth, bright enough for the world's largest observatories to see it clearly, and far enough from the sun to permit sustained observation. On December 19th it happened. The comet reached its minimum distance of 269 million kilometers, a gap vast by human measure, yet intimate by cosmic standards. From our vantage, the ancient visitor looked deceptively peaceful, a small, diffuse halo against the void, a whisper of blue still lingering in its spectrum, faint but undeniably there. For all the hype, for all the waiting, the first round of data came in quiet. The Hubble Space Telescope's initial photometric analysis confirmed what amateur astronomers had already noticed. 3IATLAS had stabilized. Its brightness curve was smooth, declining predictably with distance from the Sun. No flares, no erratic behavior. The rotation period measured roughly 7.3 hours, consistent with earlier estimates. Yet inside those predictable numbers, something subtle was off. Micro-variations in brightness, rhythmic and recurring, like a heartbeat faintly pulsing through the data. The James Webb Space Telescope offered the first major clue. Using its near-infrared spectrometer, Webb mapped the thermal emissions across the comet's surface. The results surprised everyone. Instead of a uniform temperature gradient, hottest on the sunward side, cooler on the night side, Webb detected hotspots in patterns that made no thermal sense. The warmest areas weren't facing the Sun at all. They rotated in and out of shadow, maintaining nearly constant heat, as though something beneath the crust was regulating its own temperature. The official explanation came swiftly: localized vents. Internal cavities releasing gas in bursts, generating heat pockets that infrared instruments interpreted as stable sources. It was plausible, but it didn't explain the periodicity. Every 7.3 hours, as the comet rotated, the hotspots blinked in a pattern eerily synchronized with its spin, almost like beacons. They weren't identical in intensity, but they repeated. That regularity was the kind of order nature rarely bothers with, unless physics demands it. The Webb team shared the data with ESA's JUICE mission operators, who still awaited their own readings from late November. If JUICE's spectrometers recorded similar thermal fluctuations, it would confirm that the pattern wasn't an observational artifact. The catch: JUICE's data wouldn't arrive until February 2026, due to its slow downlink. For now, astronomers could only wait. Meanwhile, Earth's radio observatories began their listening campaign. The Very Large Array in New Mexico, the Square Kilometer Array prototype in South Africa, and SETI's Allen Telescope Array all pointed toward 3IATLAS. They swept through frequencies from 50 MHz to 10 GHz, searching for narrowband signals, repeating pulses, anything distinguishable from background noise. What they found instead was absence, absolute mathematical silence. Not even the faint hiss, typical of ionized gases interacting with solar wind. Just a quiet so clean it bordered on unnatural. That silence generated as much speculation as any signal could have. Every comet emits some degree of radio noise, charged particles, plasma interactions, static crackle from solar ionization. 3IATLAS, for reasons no one could explain, did not. One researcher half-joked that the comet was radio stealthy. The phrase caught on, not because anyone believed it, but because humor was the only way to cope with the growing unease. While professionals debated in data logs and conference calls, the public's fascination surged again. Online, the comet story evolved from curiosity to mythology. There were claims of hidden transmissions, theories about alien archives, even accusations that governments were concealing contact. Most scientists ignored the noise. They had learned their lesson from Oumuamua, the first interstellar object that had triggered similar frenzy 8 years prior. Still, beneath their restraint, even sober astronomers whispered that 3IATLAS might not be just a comet. Too many coincidences, too many numbers that lined up when they shouldn't. On December 20th, NASA held a press conference. The tone was carefully neutral. The agency confirmed no evidence of artificial activity, emphasized the importance of further observation, and presented the latest high-resolution images from Hubble. To the untrained eye, the comet looked ordinary, a glowing nucleus wrapped in a soft cloud of dust. But professionals noticed details, geometric striations, subtle arcs cutting through the coma like ghostly rings. When the raw data became public, independent analysts enhanced the contrast and found something unexpected. Those arcs weren't random, they were concentric, equidistant layers, each separated by roughly 1,800 kilometers, centered perfectly on the nucleus. Nature can form concentric shells, certain pressure waves, certain outgassing cycles, but perfect symmetry on that scale. That was new. Within days, papers began to circulate online. Some invoked MHD, magnetohydrodynamic oscillations, waves of magnetic field and plasma coupling that could, in theory, shape material into shells. Others leaned toward periodic mass ejections regulated by rotational stress. The most daring invoked mechanical resonance, a structural vibration propagating through the nucleus itself, implying a solid interior. But comets, by definition, aren't solid. They're porous rubble, loosely bound. The data didn't care about definitions. One of the Webb researchers, Dr. Janelle Ortega, phrased it bluntly in an internal memo, later leaked to journalists. If this is a natural object, it's the most stubbornly self-organized one we've ever seen. That memo went viral. The phrase self-organized became the spark for 1,000 speculative fires. Back at the Harvard-Smithsonian Center for Astrophysics, Avi Loeb and his collaborators began compiling what they called the Atlas dossier, a collection of anomalies ranked by likelihood of artificial origin. They weren't claiming it was a machine. They were simply asking, if it were, what would we expect to see? The list was chillingly similar to the facts. High structural integrity, check. Anomalous emission, check. Thermal regulation, check. Stable trajectory despite venting, check. Energy spikes correlated with stellar proximity, check. Even skeptics admitted the overlap was uncomfortable, but others, particularly planetary scientists, pushed back. They pointed to precedent, the natural weirdness of the cosmos. We've seen neutron stars pulse like clocks, one said, and galaxies twist magnetic fields into spirals 10 million light-years across. A comet acting strange isn't the universe's strangest trick. Yet for all their attempts at normalization, 3IATLAS refused to behave like something ordinary. By Christmas, the comet had slipped beyond optimal viewing for the Northern Hemisphere. Observations now relied mostly on southern facilities in Chile and South Africa. Preliminary data from the European Southern Observatory showed another subtle shift. The nickel emission line, the one that had puzzled everyone since summer, was fading, but not linearly. Instead, it pulsed, dimming and reappearing every rotation. Nickel gas shouldn't pulse. It should disperse. Unless the source wasn't uniform, unless something inside was venting periodically with mechanical precision. When that finding reached NASA's internal communication channels, debate reignited. Some demanded the release of the still classified Mars Reconnaissance Orbiter images. Others argued it would only feed public hysteria. Rumors swirled that the images had been reviewed and found inconclusive, which only deepened suspicion. By now, 3IATLAS had transcended science and entered philosophy. If it was natural, It was teaching us how little we understood about the behavior of ancient interstellar materials. If it was artificial, it was rewriting our understanding of intelligence itself, because whatever made it had outlived stars, civilizations, maybe even galaxies. In mid-December, an unexpected development gave the mystery a new layer. A small, faint object was detected near 3IATLAS, trailing it by about 4,000 kilometers. At first, it looked like a fragment, a chip flung off by outgassing, but the fragment maintained constant distance, neither drifting closer nor farther away. Observations over several nights confirmed it wasn't separating at all. It was pacing the comet. ESA analysts labeled it Atlas B, assuming a companion fragment ejected in a stable co-orbit. But privately, many admitted that the behavior didn't match known fragmentation dynamics. Comet fragments either diverge or collide. They don't hover obediently like wingmen. Yet there it was, a dim speck faithfully shadowing its parent through interplanetary space. The discovery barely made the press. Officials downplayed it as a debris clump, and attention soon shifted to the approaching holidays. But within research circles, whispers began to spread. What if that fragment wasn't debris at all? What if it was part of the system, something that detached and now followed? An observer, a sensor, a seed? It was speculation stacked on speculation, but every extraordinary revelation begins with someone unwilling to look away. As 2025 closed, humanity stood divided between wonder and skepticism. The comet was outbound, cooling, fading, its secrets still locked behind the unblinking face of science. But it had already done something profound. It reminded us that even in an age of algorithms and data, the universe could still whisper, "You don't know everything." Behind that whisper was a blue glow, a pattern of heat where no heat should be, a fragment that followed without reason, and a silence deeper than the background hum of space itself. Whether nature or intention, 3IATLAS had done what no comet before it ever had. It made us feel watched. And the strangest part, maybe, just maybe, it was. When the new year dawned, 2026, the first full year of 3IATLAS's outbound journey, the world woke to a paradox. The closer we studied the comet, the less sense it made. January skies were mercifully clear across the southern hemisphere. From the high plateaus of Chile to the deserts of Namibia, observatories resumed nightly tracking. 3IATLAS had dimmed, but not as quickly as it should have. The brightness curve still followed a power law, but the exponent, normally between 3 and 5 for fading comets, hovered stubbornly around 1.8. That meant the object retained heat far better than dust or ice could account for. The residual warmth refused to dissipate. Infrared instruments at Cerro Paranal picked up faint emissions that pulsed in rhythm with the comet's rotation, 7 hours, 18 minutes, almost to the second. The hot spots Webb had seen months earlier were still there, weaker but synchronized. It was as though something deep within was still turning, still regulating, long after solar radiation should have fallen away. The heartbeat pattern became the obsession of early 2026. Every major observatory that could track 3IATLAS joined in a coordinated monitoring campaign. The signal was faint, but real. When plotted on a graph, it wasn't chaotic. It was beautifully regular, with a stability that bordered on engineered precision. Some teams compared the waveform to rotational thermal lag. Others whispered the forbidden word, modulation. If the rhythm was artificial, it wasn't broadcasting, it was breathing. By mid-January, the JUICE spacecraft's data finally began arriving.
Its ultraviolet spectrometer readings from late November, taken when the comet was still relatively bright, contained something no one had expected: narrowband emissions near 380 nanometers, perfectly spaced, forming what one engineer described as a comb of light. Natural.
Spectra are messy, broadened by temperature and chaos. This one looked surgical, like harmonics tuned to exact multiples of a base frequency. The discovery leaked within a week, and though NASA and ESA both declined comment, the papers were already circulating among research groups. The optical comb, as it came to be known, ignited every branch of speculation imaginable. To skeptics, it was a quirk of molecular fluorescence, perhaps some exotic compound of nickel and carbon monoxide interacting with solar radiation. To others, it was a carrier wave, a structured emission, deliberate, coherent. In radio terms, a signal. For weeks, the scientific community fractured into factions. One camp demanded extraordinary evidence before considering any extraordinary claim. Another insisted that waiting for proof beyond reasonable doubt was cowardice, that discovery required risk. Loeb and his colleagues stood squarely in the second camp. "If you see structure in chaos," he told a Zurich conference that February, "the burden of imagination shifts. You must first explain why nature decided to imitate engineering." The media devoured the quote. Overnight, 3IATLAS was no longer just an interstellar visitor. It was a mirror held up to human curiosity itself. But the data continued to evolve, and each new finding deepened the mystery. In early February, an amateur group in Argentina detected a brief optical flare from the comet, an increase in brightness by 0.7 magnitudes lasting just 3 minutes. Professional telescopes confirmed it hours later. The flare's light curve wasn't random. It followed the same 7-hour, 18-minute cycle, as though synchronized with the thermal pulses already observed. It wasn't enough to indicate active propulsion. No trajectory change was detected, but it hinted at internal energy release. The coincidence between the optical comb, the thermal pulse, and the flare could have been luck. But probability, once again, was the enemy of coincidence. NASA and ESA convened an emergency teleconference that month to align their public posture. Unofficially, internal minutes later, leaked by an insider, revealed the real tone. One paragraph, stark and clinical, captured the mood. If ongoing monitoring confirms periodic radiative output, coupled with structural persistence and non-random spectral harmonics, classification as a purely natural cometary nucleus will become untenable. Recommendation: consider alternative frameworks for interpretation. Alternative frameworks? The phrase was bureaucratic, careful, but everyone knew what it meant. Around the same time, data from China quietly reappeared. The Purple Mountain Observatory resumed posting positional logs, dry numbers, nothing more. But careful readers noticed something. The timestamps implied continuous monitoring, even during the blackout months. The gaps had been in public disclosure, not observation. The implication was obvious: someone somewhere had data they weren't ready to share. By late February, 3IATLAS had crossed the orbit of Mars on its way out of the solar system. Its halo shrank, its color shifted to a dull gray. It looked dead again. But the silence around it now felt performative, like the pause between acts in a play that wasn't finished. Then, almost unnoticed at first, came the oddest report yet. The companion object, Atlas B, the faint speck that had followed since December, had changed position. Not drifted, repositioned. Its separation from the main body had increased by nearly 12,000 kilometers over 3 weeks, then stabilized at a new constant distance. It wasn't tumbling away. It was maintaining formation flight at interplanetary scale with no detectable thrust. Even for those clinging to natural explanations, that one was hard to swallow. Gravitational coupling couldn't hold two fragments in such perfect relative motion. Outgassing forces should have pushed them apart. And yet, Atlas B moved as if choreographed, preserving its angle relative to the Sun and the primary body. For the first time, serious researchers began to speak in whispers about non-gravitational coherence, a phrase that meant essentially, we have no idea. In March, when the comet passed the orbit of Jupiter, its thermal pulse weakened, then disappeared altogether. Whatever engine or mechanism or natural resonance had powered its heartbeat went silent. By April, the nickel emission line was gone, the blue hue extinguished, and 3IATLAS was no brighter than an ordinary interstellar pebble, fading into night. But the silence it left behind was deafening. Conferences debated it, papers dissected it, models were built and broken. Some predicted the object would return in 27,000 years on a distant loop. Others claimed it would never come back, destined to wander the galaxy forever. A few even speculated it would alter course once more, unseen by us, as if continuing an ancient itinerary. No one knew. By mid-year, public attention had waned. News cycles moved on, wars, elections, markets reclaimed the headlines. The comet receded from both the sky and our daily awareness. But in laboratories, in quiet offices with too many sleepless nights, scientists still wrestled with the data that refused to fit. And somewhere, in a secure server farm in Pasadena, a dataset remained unreleased, the missing Mars orbiter images. Rumors persisted that they showed something faint near 3IATLAS during its closest approach to the red planet. A transient flare, geometric, too clean to be noise. If true, it would rewrite everything. But the images never surfaced. By December 2026, 1 year after its closest approach, 3IATLAS was little more than a dim whisper of light in the outer solar system, fading beyond the reach of all but the most powerful instruments. The heartbeat was gone. The optical comb was gone. The companion speck, Atlas B, was still faintly visible, trailing like a shadow that refused to vanish. The official consensus hardened into ambiguity, anomalous but natural. The phrase that science uses when it has run out of language. Yet, in one unpublicized observation from early November 2026, the Subaru telescope in Hawaii recorded something peculiar. A narrow beam of reflected sunlight flickered across its detectors, a glint from Atlas B, brief but precise. Its polarization angle matched polished metal, not rock or dust. The report was quietly archived, labeled Instrumental Reflection, and forgotten. For now. Because every story like this ends the same way, with the object leaving and humanity left staring after it, holding more questions than answers. But 3IATLAS was different. It didn't just pass through our solar system, it passed through our certainty. It taught us how fragile our definitions are, how easily natural and designed blur when the universe decides to remind us that it's older, stranger, and infinitely more patient than we are. In the silence that followed, one truth lingered. Sometimes the most intelligent thing the universe can do is nothing at all. And in that nothing, we listened, hearts synchronized to a rhythm that may never sound again. The years after 3IATLAS faded were strangely quiet. By 2027, the comet had dwindled to a mathematical ghost, too dim for any telescope to resolve, tracked only through predictive models and the faint tug of its gravitational echo on passing solar wind. To the casual observer, it was gone. But to those who had watched it, who had wrestled with its contradictions, it never truly left. It became a haunting, an open question, orbiting the collective mind of science. In the months following its disappearance, the scientific community settled into what historians would later call the interregnum of doubt. The peer-reviewed papers that followed were careful, surgical in tone, almost fearful of adjectives. Titles like Spectral Anomalies in Interstellar Object 3IATLAS, A Comparative Analysis, and Nonlinear Polarization in Non-Standard Cometary Emissions filled the journals. Every conclusion ended the same way. Further data required, but there was no more data. The object was gone, outbound into the dark at over 40 kilometers per second, slipping beyond the reach of even Webb's sensors. For a while, the debate subsided. The press moved on, government stopped funding dedicated follow-up missions, and even Avi Loeb began focusing on the next generation of observatories. But the mystery refused to decay. Like a faint radio pulse echoing through static, it persisted in fragments, academic footnotes, quiet conferences, whispers over coffee after midnight. Every scientist who had touched the data seemed to share the same unease. We saw something that shouldn't exist, and then we lost it. The silence around the unreleased Mars. Reconnaissance. Orbiter images grew heavier with each passing year. Occasionally, someone would file a Freedom of Information request. Each time, the answer was the same: no records responsive to this request. Officially, that meant the data either didn't exist or wasn't classified under that name. Unofficially, it meant whatever the orbiter saw was still considered sensitive. The reason why remained unspoken. In 2028, a graduate student at the University of Melbourne, Elena Varga, published a controversial paper revisiting the optical comb phenomenon. She had cross-correlated the spectral data from JUICE with archived readings from Soho and Punch, and noticed something that had been missed. The harmonic spacing of the light frequencies wasn't arbitrary. When plotted on a logarithmic scale, the spacing ratios approximated powers of 2. In other words, binary intervals. Her conclusion was cautious. While the observed pattern may arise from nonlinear photochemical feedback, the correspondence with binary spacing warrants further examination. The world barely noticed the publication, but among astronomers it landed like a quiet detonation. The idea that the optical comb might encode information, intentional or not, rekindled the old unease. Within months, several research groups independently verified her analysis. The harmonics were real. The binary spacing was real. What it meant, if anything, was unknowable. But the odds of such precise harmonic intervals emerging from random molecular emissions? Less than 1 in 10 million. The debate flared again. Was it a coincidence? A quirk of resonance? Or had 3IATLAS left a signature behind, a calling card written in light, hidden in plain sight? The SETI community cautiously stepped in. They weren't claiming intelligence, but they couldn't dismiss the data either.
If a civilization wanted to leave a mark without transmitting words, something timeless, immune to entropy, it might use physics itself. Frequencies don't erode, ratios don't age. A binary harmonic cascade would outlast empires. For the first time, SETI and traditional astrophysics found themselves sharing the same table, asking the same question. What if this was never meant to be understood immediately? What if it was meant to be found? Yet science moved slower than wonder. Funding waned. Attention drifted. The world, hungry for immediacy, turned its eyes elsewhere. By 2030, 3IATLAS was a myth again. It joined the pantheon of unresolved phenomena alongside the WOW signal, Tabby star, and Oumuamua. College students quoted it in debates about the Fermi paradox. Documentaries painted it as a cosmic riddle, a messenger from a forgotten civilization, but in professional circles, it became something subtler, a symbol of humility. Avi Loeb retired that year. In his final lecture at Harvard, he closed with a single slide, a still image of 3IATLAS glowing faintly blue, taken on the
morning before it vanished behind the sun. Beneath it were the words, "If it was alive, it did not need to speak. It only needed to move." The auditorium was silent for nearly a minute before the applause began. But elsewhere, small groups kept watching. A consortium of universities and private observatories launched Project ECHO, a collaboration to scan the region of space where 3IATLAS was projected to be by 2035. The aim wasn't to find it visually, it was long gone, but to listen for reflections, echoes, or any perturbations in background radiation that might correspond to its passage. They found nothing at first. Then, in 2034, something peculiar happened. Anomalies appeared in deep space microwave readings from the Planck Next Survey satellite. Faint, repeating distortions, regular dips and rises in the cosmic background aligned precisely with the path 3IATLAS would have taken if it had adjusted course by 0.3 degrees in 2027. The pattern wasn't strong enough to prove anything, but it was rhythmic. Once again, 7 hours, 18 minutes. The pulse had returned. It was weaker, more diffuse, but unmistakable. The same heartbeat that Webb had seen in infrared 9 years earlier, now echoing in microwaves halfway across interstellar space. Natural? Possibly. But no known physical process could produce a stable, periodic signal over that timescale without an internal energy source. Project ECHO released a preliminary report but stopped short of claiming discovery. They called it a repeating thermal anomaly of undetermined origin. The scientific language was careful, sterile. But everyone who read the paper could feel what the authors were too cautious to say. It's still alive. The world didn't erupt this time. The age of cosmic hysteria had passed. But among those who remembered, who had lived through the first flare of 2025, the news carried a strange calm. There was no panic, no feverish speculation, just quiet acknowledgement. Whatever 3IATLAS was, it hadn't died. It had simply gone home. By 2040, humanity's telescopes were 100 times more powerful. AI-assisted interferometry could resolve objects far beyond Pluto. Yet 3IATLAS remained invisible, a phantom in the models, a ghost in the numbers. It had become the universe's most eloquent silence. In the end, perhaps that was the point. Maybe the message was never in words or signals or harmonics. Maybe it was in the act itself, the arrival, the impossible behavior, the disappearance, and the patience of whatever or whoever had set it in motion. It didn't announce itself. It didn't conquer or communicate. It simply passed by, long enough for us to notice, and long enough to remind us that intelligence doesn't always mean noise, and purpose doesn't always mean presence. The last sentence of the Project Echo archive says it best. If 3IATLAS was a machine, it was built for endurance. If it was alive, it was built for silence. And if it was neither, then the universe itself has learned to imitate intent. By then, humanity had sent out its own messengers, small probes carrying binary harmonic signals modeled on the same ratios Varga had discovered. They were called Atlas seeds. The first launched in 2041, aimed toward interstellar space, bearing a simple inscription, "We heard you." And somewhere, far beyond the fading light of the sun, something kept moving, steadily, rhythmically, without explanation, not waiting, not answering, just continuing. By the mid-21st century, 3IATLAS had transformed from a scientific anomaly into a cultural monument. It wasn't a comet anymore, not in the minds of those who had grown up hearing about it, but a symbol of something larger, something that reached beyond physics and data. Teachers used it to explain the limits of observation. Philosophers cited it as proof that mystery itself was an engine of progress. Every generation has its defining question, and for humanity in the 2040s, it was this. What was Atlas? No one could agree on an answer. But that disagreement had become the point. After the launch of the Atlas seeds, those small message-bearing probes inspired by the harmonic code, humanity found itself united in an unexpected way. For the first time, exploration wasn't just about curiosity or conquest. It was about conversation, even if the other side never answered. The phrase, "We heard you," became a quiet mantra, engraved on mission patches, written on spacecraft hulls, whispered by engineers before launches. It wasn't faith exactly. It was recognition, a nod to the possibility that we were not the first to wonder. The seeds themselves were masterpieces of minimalist engineering, tungsten shells, each carrying a lattice of binary intervals encoded in physical ratios rather than electronic storage. They contained no words, no images, no instructions, just math and rhythm patterns that would survive radiation, time, and entropy. A message written in the only language that never dies, proportion. As humanity sent them outward, 10 seeds by 2045, 50 by 2050, they began to form a distributed monument to that first encounter. Not proof of alien intelligence, not evidence of gods or ghosts, but a gesture. We noticed and we learned from your silence. Meanwhile, the scientific consequences of 3IATLAS rippled across disciplines. The comet's irregular polarization and thermal data inspired whole new fields of study. Materials science developed phase-stable alloys, modeled on its impossible heat retention. Aerospace engineers used its rotational resonance patterns to design spacecraft hulls that could dissipate stress in rhythmic pulses. Even medicine found applications in 2048. A biophysicist at Kyoto University cited the comet's self-regulating thermal balance as inspiration for the first artificial cell membrane that could maintain temperature homeostasis without external input. In short, 3IATLAS had become a teacher. The irony, of course, was that no one ever proved it was artificial. Decades of analysis, simulation, and theoretical modeling failed to produce a consensus. But that uncertainty itself became the foundation of a new scientific philosophy, the principle of anomalous humility. It held that when faced with phenomena beyond current comprehension, The correct response wasn't denial or speculation, but patience. Observation before interpretation, silence before certainty. The universe, it turned out, was far more articulate in its enigmas than in its answers. Still, not everyone accepted the quiet. By the 2050s, an entire movement had emerged, the Atlas faiths, as sociologists later called them. These were not religions in the traditional sense, but new schools of existential philosophy that treated 3IATLAS as a kind of cosmic parable. To the order of the harmonic ratio, the comet was a divine algorithm, a mathematical manifestation of the universe's consciousness. To the Church of the Returning Light, it was a messenger, a seed sent long ago to awaken civilizations once they reached technological maturity. And then there were the silents, those who believed 3IATLAS was neither alive nor divine, but deliberate, an instrument built by something ancient that no longer existed. For them, the lesson was not to worship, but to endure. If it survived 10 billion years, one silent text read, then endurance is holiness. Their rituals were simple: silence, reflection, and the repetition of a rhythmic breath cycle, 7 hours, 18 minutes, divided proportionally into seconds, honoring the comet's pulse. To outsiders, it looked absurd. To the silence, it was communion. Meanwhile, astronomy moved on. New interstellar objects were discovered, 4I Selene in 2038, 5I Kuznetsov in 2044, but none behaved like Atlas. Each was studied obsessively, yet they all followed the expected laws: normal outgassing, predictable light curves, standard compositions. Nature had returned to normal, as if the universe had granted one brief glimpse of the impossible, then closed the curtain. But some data refused to stay buried. In 2057, on the eve of the 30th anniversary of Atlas's discovery, the Mars orbiter images were finally declassified, not through government transparency, but through a cyber leak by an unknown source. The release included only 6 frames, grayscale and blurred, taken in early October 2025, when the comet had passed near Mars. 5 of the images were unremarkable, a bright nucleus surrounded by dust. But the 6th frame, taken at 0511 UTC, showed something extraordinary, a small angular reflection just beside the nucleus. Not a natural fragment. Its geometry was too precise. A triangle, symmetrical, reflecting light from the sun at an intensity far greater than the comet's surface. The structure was tiny, perhaps 20 meters across, and gone in the next frame. NASA immediately denounced the leak as digitally altered, but independent photometric analysis confirmed that the image contained no trace of manipulation. The data was real. For the next year, the world relived the frenzy of 2025. Was it an artifact, a shadow, a satellite glitch? Or had Atlas revealed something we were never meant to see, something it carried, something it released? Theories blossomed like wildfire, and just as before, the official narrative folded itself into ambiguity, insufficient evidence for interpretation. But to those who remembered the pulse, the binary light, the companion fragment that followed and then disappeared, the answer felt less distant. The triangle, they said, was B, the companion, the watcher, the one that stayed behind until the last moment. By 2060, a generation of young scientists had grown up with Atlas as mythology, a ghost story for rational minds. But unlike myths of old, this one came with equations, spectra, data points. It was a legend you could graph. At the University of Oslo, a young astrophysicist named Rebecca Holm published The Persistence Hypothesis. In it, she argued that Atlas's behavior could be modeled as a closed-loop system designed for thermodynamic endurance. It didn't need fuel or propulsion. It only needed a cycle, a way to oscillate between energy states using stellar flybys as periodic recharging points. "It's not a traveler," she wrote, "it's a pendulum." Her paper proposed something radical, that Atlas might still be out there, looping through interstellar space on a trajectory designed to intersect star systems every few million years, harvesting solar energy to sustain itself indefinitely, a self-sustaining relic of cosmic engineering. Her hypothesis was unprovable, but it captured imaginations. Soon universities were teaching Atlas dynamics as part of advanced astrobiophysics. AI simulations modeled thousands of possible trajectories, predicting that if Holmes' cycle was correct, 3IATLAS would pass near the binary system TRAPPIST-1 in the year 9141 CE, 10,000 years from now, a blink in cosmic time. Somewhere, a new civilization might be watching the sky when it arrives, asking the same questions we did, and perhaps that was the legacy, the recognition that 3IATLAS wasn't just an object, but a story written across epochs. It connected us not only to the cosmos, but to the future itself. Because one day, someone else will see that faint blue glow and wonder, who built this? Who sent it? And why does it still move? We may never know if Atlas was a comet, a probe, or something stranger, but we know what it did to us. It taught us to build patiently, to observe humbly, to listen carefully. It showed us that the universe's greatest messages might come not as signals, but as questions that refused to die. And in that endless question, humanity found something it had been missing all along, a sense of belonging, not in the answers, but in the asking. Some say Atlas was a messenger, some say it was a mirror, but maybe it was both. Because when we looked at it, truly looked, what we saw staring back wasn't alien intelligence at all. It was ourselves, curious, enduring, and infinitely small against the silence of forever. By the middle of the 22nd century, the mystery of 3IATLAS had become less a puzzle to be solved than a rhythm that human civilization had learned to live with. The old astronomers had passed on, but their equations survived in archives, their doubts preserved in data. Children learned about Atlas in school, not as a comet or a probe, but as the first question that never stopped moving. 1. The age of listening. By 2110, deep space interferometry had reached the edge of imagination. Earth and its colonies on Luna and Mars operated a linked array the size of a solar system called the synoptic ear. It could detect fluctuations in background radiation down to the energy of a snowflake. Every few years, someone pointed it toward the dark lane where Atlas had gone. Every few years, the same 7-hour, 18-minute modulation trembled faintly through the noise, never stronger, never gone. No one called it a signal anymore. It had become the baseline hum of the universe, the heartbeat against which other anomalies were measured. If it was alive, it was sleeping. If it was built, it was patient. The synoptic ear taught humanity a new form of faith, observation as devotion. Generations of scientists maintained watch, knowing they might never know. The act itself became sacred. 2. The culture of the seeds. By then, thousands of Atlas seeds had been launched. Some failed, most vanished. A few sent back whisper-weak telemetry from the void. They carried no messages except ratio and rhythm. Yet civilizations built whole literatures around them. Artists composed symphonies timed to the comet's rotation.
Architects designed temples whose halls pulsed with faint light every 7 hours. Pilgrims sat in orbital habitats, breathing in cycles that matched the ancient waveform. Even secular culture, always skeptical, always forward, kept the cadence. Every new ship that left Earth carried a plaque engraved with the same phrase: "We heard you, and we waited." By 2150, waiting was no longer seen as passivity. It was the highest form of participation, a way of staying synchronized with the universe's longer tempo. 3. The return of B. In 2183, the mining station Perihelion 3 detected an object approaching from the direction of the outer Oort cloud. It was small, only 30 meters across, and traveling faster than any natural fragment should. Initial readings showed high reflectivity, perfect geometry, triangular symmetry. The world held its breath. For a week, the object coasted silently toward the inner system, decelerating ever so slightly, as if responding to gravity with intelligence. Then, before instruments could triangulate it, it shifted trajectory and vanished into the heliopause, gone again like a thought half remembered. Official reports called it debris from a failed seed probe. Unofficially, among the observatories that had tracked it, one line appeared in a private log: signature match, 3IATLAS B. It was never confirmed. It didn't need to be. The echo was enough. 4. The philosophers of resonance. By 2200, a new branch of thought, resonant philosophy, had grown from the Atlas legacy. It rejected the binary of natural versus artificial, proposing instead that intelligence was a pattern that could emerge anywhere the universe learned to repeat itself: a pulse, a rhythm, a persistence against entropy. Under this framework, 3IATLAS was neither comet nor craft. It was a pattern that had learned to survive, a mirror not of civilization, but of continuity itself. To the philosophers, the lesson was profound. If intelligence is defined by endurance, then everything that persists carries a trace of mind. Stars, atoms, comets, each an experiment in remembering form. And so humanity stopped asking what Atlas was and began asking how it had endured. The answers they found transformed engineering, biology, even ethics. Technologies of longevity were modeled on its thermodynamic equilibrium. Societies reorganized around cycles rather than progressions, understanding that survival, not speed, was the truest intelligence. 5. The last transmission. In 2279, nearly 2 centuries after Atlas's first appearance, the synoptic ear recorded something different. The 7-hour rhythm faltered once, then doubled, an echo of its own pulse like 2 hearts overlapping. It lasted for only a single rotation. Then silence returned, thicker than before. The analysts debated endlessly: interference, cosmic ray. Or was it an acknowledgement, a final rhythm folded back upon itself saying, "I heard you too"? The data was inconclusive, it always was. But that didn't matter anymore. Humanity had built entire worlds on inconclusive data. The point was not the answer. The point was the echo. 6. The long memory. By 2400, human colonies stretched across a dozen systems. On each, observatories kept a ceremonial alignment with the coordinates of Atlas's trajectory. Every 7 hours, 18 minutes, they blinked a soft blue light toward the void. Not to call it back, but to remain part of the pattern. Children born on distant worlds learned that their ancestors once watched a visitor cross the sky and chose to answer not with fear, but with rhythm. That was their creation myth, the day humanity decided that silence could be dialogue. In the Great Library on Ceres,
A single preserved artifact sat beneath glass, a tungsten plate from one of the earliest Atlas seeds. The inscription, worn but legible, read, "Between stars, silence is speech." 7. The last observation. In the year 10,000 CE, long after Earth's surface had cooled into museum continents and most of humanity had scattered among the stars, a small observatory orbiting TRAPPIST-1b recorded a faint blue flare on the edge of its system. Periodic, symmetrical, lasting 8 days. The young astronomer on duty didn't know the story of Atlas. She simply logged the anomaly, labeled it 3I Visitor, and sent the data to the archive. Her note at the end of the report read, "Possibly artificial. We'll continue monitoring." She could not have known that 10 millennia earlier another species had written those same words. And thus the cycle continued. When we look back across the centuries, 3IATLAS stands as both a mystery and a mirror. It never spoke, yet it taught us to listen. It never stayed, yet it made us endure. It may have been built or born or simply existed by accident, but whatever it was, it changed the rhythm of our species forever. Because in its silence, we found music. In its distance, we found belonging. And in its endless motion, we learned what it means to be alive, to move forward, quietly, together, into the dark.